I am Gandani, and we are waiting for Mr. Marcel. I don't know. I don't know where it is. Ah, here we are.
All right, so should I start?
Yes, yes, we are alive.
Okay, let me expand my screen.
Yeah,
Hello? Okay, I'm starting now. I'm starting.
yes, start.
Hello. Good afternoon to all the listeners. My name is Miracle Chibuzor Marcel, and I'm the founder and the director of the Pan-African Citizen Science E-Lab. So today we are going to be discussing on white dwarf stars, okay? And that is the fifth series, our fifth star series. So in our table of contents, I'm going to be introducing white dwarfs. Then I will go back to the stellar life cycle to describe where white dwarf is coming from. Then I'll talk about types of white dwarfs. Then I'll discuss features or the properties of white dwarfs. Then I will explain cataclysmic binaries, okay, and novae. Then I'll also explain type 1 supernovae. I'll talk about white dwarf mergers and other facts about white dwarfs. So, what are white dwarfs? White dwarf is a dense, compact stellar remnant left over after a low mass star, example, our sun, has exhausted its nuclear fuel. So, simply put, a white dwarf is a dead star, okay? A dead star. Just like we have a neutron star is a dead star, black hole is a dead star, but a neutron star and a black hole are remnants of high mass stars. High mass stars are stars that have from 8 solar masses, 8 times the mass of the sun and above. Okay, so those are the high mass stars. But for low mass stars, when they die, they form white dwarfs, or can call them white dwarf stars. And why do we call them white dwarfs? Is because they are white. They look very white and very bright. That is why we call them white dwarfs. So revisiting the stellar life cycle, when we started describing about stars, I told you that stars form from the collapse of giant molecular clouds. From there, they migrate to the protostar stage. Now, depending on their masses, they either become high mass stars or small stars, just like you are seeing here. But like I told you before, a white dwarf emanates from a low mass star, so it is going to go through this route. So it's going to become a small star. Okay, from there it evolves to a red giant, and from there it evolves to a planetary nebulae. It is going to shed off its surface and becomes a planetary nebulae, and then settle as a white dwarf. So I'm going to explain this process in detail. Okay, although I have explained it before in our first and second lecture on star series, but I'm going to just revisit them so that you can have an idea of how white dwarfs come from. So here is a diagram of a low mass star, just like our sun. Okay, it has a core and it has other layers. Okay, you can see this is a chromosphere, this is radiation zone, this is convection zone, this is the photosphere, and this is the corona. Okay, so initially, look at this. Initially, when the star begins to fuse hydrogen in the core, all throughout from the top to the bottom is predominantly hydrogen. Listen to my term, predominantly hydrogen, but there are different layers. So the core you are seeing right now is hydrogen core. Okay, so now as the hydrogen begins to fuse, it is going to produce heat and helium. Okay, so that heat is used to sustain the structure of the star, because the overall weight of the materials are trying to fall in, okay, while the heat, the radiation pressure coming from the heat is pushing it out. So at some point, the star is going to find a balance. So hydrogen is going to continue fusing to produce helium and heat. But I'm mostly interested in helium. So in the diagram that you are seeing right now, the brown is hydrogen, okay? And the other color, I think that's mauve. I can't remember. Okay, violet color. So that is helium. So and this flash you can see here is the fusion. It is happening right at the core. So as hydrogen is fusing, it is fusing to produce helium and heat. The helium is going to start building up like an ash around the initial hydrogen core. Okay, it is going to be building around, it's going to start forming its own core around the initial hydrogen core. So, but hydrogen we continue to fuse to helium and heat. So the quantity is going to deplete over time. It is going to deplete over time. So you can see from the diagram here, the brown circle is the hydrogen quantity. It is depleting. And now the size of the helium core is increasing. It is increasing in thickness and in size. So, but the fusion continues, okay? So now, as this happens, you know, helium is heavier than hydrogen. So this helium ash is going to be contracting. So it is going to be contracting. So there are two processes that add heat to the star, the contraction and the fusion. These two processes are adding heat to the star. So this process is going to continue until this stage where you now have predominantly helium core. You have predominantly a helium core. Okay, so at this stage, we say the hydrogen in the core has exhausted. Okay, so the star will stop, you know, producing heat. But the heat that will sustain the star is due to the contraction. The contraction. So look at this diagram here. You can see it. You now have a core. Now, this helium core is going to continue to contract until it reaches 10 million Kelvin. Remember, 10 million Kelvin from our last lecture, I described it as the temperature needed to ignite nuclear fusion. I mean, hydrogen to hydrogen fusion, okay? So as this core contracts, it is going to add heat to the surrounding, There are hydrogen in the surrounding. Look at it here, hydrogen in the surrounding. So once it hits the temperature beats 10 million Kelvin, so which is enough to fuse the hydrogen. So this hydrogen here at the outer layer, we call that hydrogen, the shell, okay, will begin to fuse. So the process will continue, okay? So the hydrogen will fuse, more ash will be deposited to the helium core. So the helium core becomes larger and larger. So at this point, it is no longer a main sequence star, okay? It is no longer a main sequence star. And also, the star will begin to inflate, to begin to move away to the red giant phase. I'm going to show you that later, but understand this process. So this is going to continue until, so this is going to continue like this So look at this yellow line here. I drew this diagram. This yellow line is the fusion. So the hydrogen is fusing and producing more helium, and it is depositing the helium here. So the core is getting larger and larger. Okay. So here the brown is the hydrogen. So the process continues. The star will be inflating. Do you understand? The core will continue to contract, and the temperature will even surge higher. So that is going to happen until we reach 100 million Kelvin. That is the temperature required to ignite helium fusion as a core. So this helium core will begin to fuse, okay? And when helium starts to fuse, it starts giving rise to carbon, oxygen, and heat. So I have just used this dark line to signify the carbon production. So the black center is the carbon production. So this process is going to just repeat, just like helium core formed. There is going to be a carbon core. Okay. So that's the process. That's just a summary of the process. So this is when the star is formed. So this is the main sequence stage. So the main sequence stage is basically when hydrogen is still fusing at the core. But once there is hydrogen fusion outside the core at the shell, so that is when it starts migrating to this red giant phase. Okay, so and then it becomes bigger. Now, as it gets bigger, it is going to get brighter. The radiation is going to become more because the contraction is increasing. The fusion, helium fusion gives more heat. Helium fusion gives more heat than hydrogen fusion. So there is going to be more radiation from the system. So the radiation is going to overpower the infalling matter, the outer layer. So this star is going to shed off its surface. Okay, so the physics is complicated. I described it fully in our second series on stars. Okay, so by the time it has finished, shedding off its surface, it has shed a ton of its total mass. Okay, it is going to just remain only the carbon core. Now, no matter how carbon core fuses, it is not going to produce enough heat to fuse carbon. Okay, to fuse carbon, you would need about 600 million Kelvin. So the weight of the core is not going to be enough to fuse the carbon. So it is going to have a carbon core left out. So types of white dwarfs. So that is just the process of white dwarf production. I just described it. So now in the types of white dwarfs, we have carbon oxygen white dwarf, which is just what I described. Okay, carbon oxygen white dwarfs, and the kind of stars that produce the progenitor stars that oxygen white dwarfs have masses between 0.5 to 8 solar masses. Okay, now these we have observed white dwarfs before. Okay, we have observed them. We have white dwarfs presently. Okay, for white dwarfs, typically it takes around 10 billion years for the hydrogen fusion at the core to finish. Like for our sun has fused hydrogen for the past 4.5 billion years to 5 billion years. So it still has an extra 5 to 6 billion years to continue fusing hydrogen in the core. Okay, so it's around these 10 billion years to fuse it. So now we have another type of dwarfs. Hidden white dwarfs are from very low mass stars. Okay, those very low mass stars, they have masses from 0.08 to 0.5 solar masses. So that is just the minimum mass of stars to 0.5. Okay, but these stars are hypothetical. They are hypothetical because they fuse hydrogen very slowly. So it's going to take them about 1 trillion years to fuse hydrogen in their core to be able to have a helium white dwarf. So they are basically theoretical, okay? So, you know, our universe is about 13.8 billion years. So we don't have any helium white dwarf at the moment. It is just hypothetical. So all the white dwarfs I'm going to describe in this video that are, in fact, that are being described in the science community are basically these carbon oxygen white dwarf, because 10 billion years is at least less than the age of the universe, and we have a lot of white dwarfs. So features of white dwarfs: mass. One of the first features of white dwarf is the mass. White dwarfs have minimum mass of 0.17 solar masses. Okay, the ones that have been observed, 0.17 solar masses. And their maximum is about 1.33. Remember that this maximum is called the Chandrasekhar limit. Okay, it is also, remember, 1.4 solar masses is the minimum mass of neutron stars. So you're now having a maximum mass of white dwarf being 1.33. If you add more matter on a 1.33 solar mass white dwarf, it is going to collapse and become a neutron star. So in practical, most observed white dwarfs have masses between 0.6 solar masses. That is just the most observed masses they have, okay? Or we have more, but the ones that we have observed so far is 0.6 solar masses. So how about the size? How about the size? Remember what I talked about, the mass being 1.33, almost like the mass of the sun, just a little bit above. In fact, it is good that it is above the mass of the sun, 1.33. So it is, we can imagine it as the sun, okay? And now, here is the planet. We live here, look at that. That is our planet. So I am bringing this into perspective because I want to describe to you something. I want to tell you that a white dwarf is just the same size as the Earth. So you can literally, so to form a white dwarf, you're going to compress the sun. So imagine compressing the sun, the whole weight of the sun to the size of the Earth. So you can imagine that. That's very crazy, right? So compressing the whole sun into Earth. So that is just the size of a white dwarf. So white dwarfs are just similar sizes as Earth. So they are pretty dense, okay? So now explaining why they have this small size, okay? Remember, I have described it before, that hydrogen fuses into helium. Then helium fuses into carbon and oxygen. Then we have assorted electrons, okay? Now, unlike okay, they suddenly collapse and explode into supernovae. White dwarfs, low mass stars, do not explode. Rather, they shed off their surface, okay? As they are shedding off their surface, they are contracting. Do you understand? They are contracting and producing heat ahead. That is how they, now, this contraction, remember I told you that the assorted electrons and other ionic materials on a white dwarf. So there are Coulomb forces, okay? So now as this white dwarf is contracting, it's going to overcome this Coulomb force. It's going to overcome this Coulomb force. Then there's another force, another pressure called degeneracy pressure. So from the electron, it is coming from the electron. So sorry for that. Now, this contraction is going to be stopped by this electron degeneracy pressure. So this electron degeneracy pressure obeys polar exclusion principle. I have described it when I was talking about neutron stars last week or last 2 weeks. So understand the polar exclusion principle. So you can imagine soldiers spaced out, okay? So you can imagine these soldiers as fermions because electrons and neutrons are fermions, okay? So they are spaced out, but under high pressure, just like a white dwarf, they're going to be squeezed together like this until you reach a point you can no longer squeeze them. At least two persons cannot occupy the same position. So that is just the idea of the polar exclusion principle. So you squeeze material, there are some levels you cannot squeeze them. So that is just a quantum mechanical phenomenon. So like I described before, that white dwarfs, you compress the vast mass of a sun to the size of Earth. That will give you a white dwarf. Okay, so white dwarfs are pretty dense. They are very, very dense. So the average density is far less than atomic nucleus. Remember, when I was talking about neutron stars, I said is equivalent to the density of white dwarfs. Their average density are far, far less than that of neutron stars, and also far, far less than atomic nucleus. So white dwarfs are second in line in density to neutron stars in the universe, okay? So one sugar cube size of a white dwarf weighs 1 ton on Earth. One sugar cube size, it weighs 1 ton on Earth. And if you want to imagine what 1 ton is, 1 ton is equivalent to the weight of a car or an elephant. So that is just what 1 sugar cube is. Now, how about the spin? How about the spin? So, just like I described with neutron stars, the high spin rate of neutron stars is due to the conservation of angular momentum, just this equation. So the angular momentum is equal to the moment of inertia times angular velocity. So the moment of inertia depends on the radius, okay? It depends on the radius. So if you reduce the radius, you say that the moment of inertia has reduced, okay? So now when a white dwarf is formed, it is smaller than the progenitor star. So you can say that the radius has reduced, okay? So that will make, according to the law, that conservation of angular momentum, that's going to make the angular velocity to increase. So the spin is going to be very high. So you have a sun-like stars. So the progenitor star, their spin, it takes them about 10 to 30 days to complete one spin, one rotation, okay? But for white dwarfs, they just take few hours to several days. So if you compare that to neutron stars, which are milliseconds to 8 seconds, and the reason is because neutron stars are sized like cities, the size of a small city. So this is Earth. I can see Brazil from there. I can even see the United States from there. So you can imagine a small city in the United States, and that is the size of a neutron star. So you have to continue compressing this white dwarf until you can compress this white until you get a neutron star. Okay, so that is why they have high spin rate, but not compared to neutron stars. So I showed you this demonstration. So watch as the Earth, I use Earth, but this generally applies for all spheres, okay? I just used Earth here, but it applies for all spheres, so don't misunderstand me. So if I reduce the size of Earth, remember I'm not zooming in, it is just the same size, sorry, the same orientation, but the size of the Earth is going to be reduced. The radius is going to be reduced. So watch it now. It is going to be reduced. So as it's reduced, the moment of inertia is going to increase. It's going to reduce, and then that is going to show up the angular velocity. So that is just the idea. So how about the magnetic field? The magnetic field. So let us compare it. For Earth has a weak magnetic field, okay? It is between 25 to 65 micro Tesla. For the MRI machine used to scan the human body, it has a magnet about 1.5 Tesla. The magnet is very powerful if you are put into that technology before, into that system. For a lab magnet, the one we use at CERN is up to, from 8 to 10 Teslas. So that is very crazy. Now, for our white dwarf, the magnetic field is about, the average is about 100,000 Teslas. So that is about 1.5 million times stronger than the magnetic field of the Earth. Now, this magnetic field is not due to the charges and the spin of the white dwarf, unlike what we saw for neutron stars. The reason for the high magnetic field of neutron stars is because of the electrons, the ionic materials, and high spin of neutron stars. But in this case, it is not because of that. It is because of the inherited magnetic field of the progenitor stars. So stars, when they have a given, they have magnetic field around them. Okay, so now when you now have a white dwarf, the size is reduced. So the magnetic field is going to be amplified. It's going to be amplified. So here is the cross section of the interior of a white dwarf. So about 30 kilometers thick. You're going to have hydrogen in the plasma phase, some plasma. Okay, then then we have 260 kilometers beneath the interior. We're going to have helium. Then the rest is carbon and oxygen core. So predominantly carbon and oxygen. So how about gravity? How about gravity? The surface gravity of 1,000 to 1 million times that of Earth. Okay, so it is very, very high, relatively high, but not as high as that of neutron star. So if you drop an object, by the time it reaches the surface of a white dwarf, it was have attained a final velocity that is about 17 times the speed of light. 17 times the speed of light. That value, that 17 times the speed of light, is also the escape velocity on the surface of a neutron star, of a white dwarf. So if you want to throw something off, if on the surface of a white dwarf and you want to throw something, you have to throw it with an initial velocity of about 17% the speed of light. Now, how does gravity bend light around white dwarf? To understand it, for a black hole, if you are viewing a black hole, if you are closer to a black hole but not too close, and you are viewing a black hole, you're going to see every inch of the black hole from one position. So because gravity, light, it bends light around it. So you're going to see every surface of a black hole from one position. For a neutron star, I described it, you're going to see two-thirds. Two-thirds is about maybe 66%. 66% of the entire surface. Because these two bodies have huge mass. They are very compact, okay? Although they may not have terrible mass, but they are very compact. So that compensates for that. Even for normal stars like our sun, they have huge gravitational attraction. In fact, that was used to prove Einstein's theory or general theory of relativity during eclipse. So it was calculated about 1.75 degrees to degree at which it bends light. So even normal stars bend light. In fact, everything bends light. Even planets can bend light. But if you compare to the degree at which normal stars bend light to white dwarfs, that of white dwarf, the degree is higher. So I can't tell you that, okay, white dwarfs bend light at a third degree, okay, or maybe I say maybe it bends light more than half. You can see more than half of the surface of a white dwarf. No, but it pretty much bends light more than normal stars. So you can see the observed star position and look at how much it has bent this light because space-time is curved. That is the idea of general theory of relativity. So now, white dwarf, also, the gravity is also high enough to produce noticeable gravitational redshifts. So it means as you are looking at a white dwarf, maybe the color is blue. By the time the light reaches your eyes or your telescope, it must have been stretched to the weaker parts of the spectrum, maybe red. So we call that gravitational lensing. That also happens for black holes and the neutron stars. So it also happens for white dwarfs. So the gravity, if you're on the surface of a white dwarf, the gravity there is it's very high that even time dilation is very, very pronounced. Okay, on Earth, time dilation is not pronounced. Okay, because the Earth gravitational pull is very weak. But for a white dwarf, the time dilation is very, very noticeable. How about spaghettification? It's a tidal effect. It's a high degree of tidal effect noticed around black holes and neutron stars. But however, for a white dwarf, the gravity is not high enough to produce this spaghettification effect like seen on neutron stars and black holes. So I can comfortably say that it is safer to travel to white dwarf than neutron stars and black hole, although it is not a good advice. You're going to still die because the temperature is very high. For a newly formed white dwarf, the temperature is above 100,000 Kelvin. Okay, so that temperature alone is enough to make the white dwarf to glow in the UV and X-ray spectrum. Now, this radiation excites planetary nebulae. Let me show you planetary nebulae here. Look at, so I told you as these fusion mechanisms, the hydrogen and the helium fusion mechanisms are going on, this more heat is produced and the radiation pressures are overcoming the weight of the infalling matter. So these matters are pushed out. They are pushed out. So they form these beautiful structures, you know, like clouds, like nebulae around the white dwarf. Okay. Now, on their own, they're not supposed to emit light. However, due to this high temperature, like I just mentioned, in X-ray, UV, these rays, these X-ray and UV rays, are high energy electromagnetic waves. They are going to excite the molecules, the atoms and the molecules around these that are components of these planetary nebulae. So when they are excited, the electrons move to higher energy state. So when they fall back, they give up those energies, you know, in other lower electromagnetic spectrum. So we see these beautiful colors. So the reason why these are shining, these beautiful colors, is due to the high radiation from the white dwarf. So here is a ring nebulae. Here is the white dwarf at the center. Here is the helix nebulae. Here is the white dwarf at the center. This particular one is the white dwarf at the center. So, but other white dwarfs, as they age, their temperatures could drop below 10,000 Kelvin. So, cataclysmic binaries, what are they? What are they? I'm going to explain them. So I have shown you this picture when I was talking about neutron stars. I'm going to describe it again and also add some few things that happen about novae, okay? Now, you have a system. We have a donor star. It could, most of the times, it is a star that is a main sequence. It has a lot of hydrogen, okay? It's still fusing. But then you have another star that has died and maybe has formed a white dwarf. Okay, it has lived out its life and died, and now it's a white dwarf. Okay, so now there are binary system. Okay, so looking at them, here is the distance between the two of them. So at this red spot, the gravity balances. It means that if an object is here, the gravity at which the white dwarf pulls it is equal to the amount of force this donor star pulls it to its side. So there's going to be a balance, okay? But if the setup is in such a way that they are much closer, okay? If these two systems are much closer than what I just described, so this red spot, we call it inner Lagrangian point, it becomes situated right inside the star, the donor star. So at that point, these other materials here from the star that are now, so there's going to be a resultant force that's going to pull the materials towards the accretor, the white dwarf, okay? So they're going to be attracted. The resultant force is going to be towards here. However, they are not going to force radially like that. This is because the two systems are rotating. So these black lines I have just described they are rotating. Okay, so these hydrogen materials are going to spiral inside. They are going to spiral around the accretor, the white dwarf, and then fall onto the surface of the white dwarf. Okay, now remember that the rate at which it falls is very high. It is falling around 17% the speed of light. So if you translate it to kinetic energy, it is very, very huge. Okay, so that kinetic energy is translated to heat. Do you understand? So as this matter is falling in, it is heating up. Remember, this is hydrogen. It is heating up the hydrogen that is on the surface of the white dwarf. Remember from the structure I just showed you, white dwarfs are made up of, the surface is hydrogen, okay? So it is heating up the surface of the white dwarf until the temperature is going to increase up to 10 million Kelvin. That is the temperature required to ignite hydrogen nuclear fusion. So there's going to be an explosion. So that explosion is going to disrupt these accretion disks. It's going to disrupt it. It's going to explode. We call that a novae. So that is the idea of the cataclysmic binaries. So after that, the whole system is going to settle. The process is going to resume again. Okay, it's going to resume again. It happens again, novae. So it happens all the time. We call that cataclysmic binaries. However, it does not stop. It does not decrease the overall mass of the white dwarf. So even if the surface explodes, some materials are still left. So the mass of the white dwarf increases, okay, until it reaches the Chandrasekhar limit, and it will explode. And it will explode. So you can imagine. So let us imagine a white dwarf that is about 0.6 solar masses. Okay. Now, when you add more mass to it, it is going to pass the Chandrasekhar limit. Okay. And that is going to result in what we call a type 1 supernova. Type 1 supernovae are as energetic as normal star supernovae. So you can still see them halfway in the universe. Now, when type 1 supernova happens, it obliterates the star. Nothing is left. So for most of these binaries, white dwarf binaries, when they explode like this, they obliterate. But in rare cases, because they know physics, in rare cases, they do not obliterate. Sometimes some things are left, some materials are left. And most of the times, what is left is a neutron star. Remember, I mentioned it last time, but majority of the time, the system obliterates. So how about white dwarf mergers? Here you have two white dwarfs orbiting each other. As they are orbiting, they generate gravitational waves, just like neutron stars and black holes. They generate gravitational waves. So white dwarf mergers or binaries like these also are sources of gravitational waves. So when they merge, they explode in type 1 supernovae. It is also a type 1 supernovae, okay? So they could form a more massive white dwarf, or they could also form a neutron star. Now, just like, so just like neutron stars, when two neutron stars, we have neutron star mergers, they initiate what we call R process nucleosynthesis. Just the same way, when you have two white dwarf mergers, they're going to have the same R process nucleosynthesis. But this time, you're going to produce elements that are above carbon in the periodic table. So, other facts about white dwarfs. Now, we have discovered about 10,000 white dwarfs in our Milky Way galaxy. And most of these discoveries are in our Milky Way galaxy because we haven't really started exploring stars in other galaxies. Now, over time, because there is now a carbon core, over time, neutron star will lose a lot of heat. Okay, it becomes a black dwarf. It's going to become a black dwarf. And this carbon core is going to crystallize into diamond, into a real diamond, because diamonds are made from carbon. So white dwarfs are also called cosmic diamonds. So the universe is very precious. A lot of precious metals are out there. A lot of precious materials are out there to explore. We shouldn't even kill ourselves for all these little materials here on Earth. So that is the end of my lecture. So in my next lecture, I will be talking about exoplanets, and that will be on Friday. So thank you so much for paying attention.